So this talk will be about geophysics as a quantitative tool, and in particular, I'm going to focus on seismic data, just like Edward, and more in particular about full waveform inversion of seismic data and what are the challenges associated to it, and a bit of in-depth reasoning about cost benefit and what it means to apply these sort of advanced data processing and inversion techniques to the data typically acquired in the context of wind farm site characterization and foundation design. Um, so First, I'm going to go through the principle of full waveform inversion, which are probably known to you from other larger scale applications or even for global seismology. And we're going to see what full waveform inversion promises. And then with respect to the characteristics of the very shallow geology and the kind of data that we acquire for very shallow geophysical investigations, we are going to see if full waveform inversion can live up to the expectations that people expect from such an advanced method. And then we're going to see a couple of examples of application to very shallow geophysical characterization. One in the context of submarine landsliding, and one in the context of site characterization for wind farm foundation design. So full waveform inversion iteratively updates a geophysical model of the subsurface with a chosen parametrization and a chosen approximation of the wave equation, which you use to approximate the data, the synthetic data. And by minimizing the misfit between the calculated data and the observed data, you improve your state of knowledge of the subsurface by injecting in the model the missing heterogeneities as they are recorded in the observed data. And it does so and it promises a maximum vertical resolution on alpha wavelengths. So if your dominant wavelength is a meter, you can hope for a resolution of alpha meter. So how does that differ from conventional approach to seismic data processing? Usually you use the travel times through velocity analysis to derive the large wavelength scale properties of the model. And then if you have a good kinematics of the subsurface, you can migrate back the reflections that you record at the data at your receivers back to the locations where they originated in a process called migration. And then conventionally, you correlate the migrated image with the geotechnical ground truth and you extend it sidewide. Um, just so we agree on the vocabulary, so from now on, I'm going to refer to this large-scale model as low frequency, spatial low frequencies, and this short-scale model as high frequencies of the model. And you see, this is an example I like because this is clearly a bear, and you can recognize it from the high frequencies only of the image, but it doesn't quite tell you the full picture of what it is. In order to do that, you need to feel what we call a wave number gap in the image, and full waveform inversion aims exactly at doing that all in one go. So is it feasible to get the broadband bare from UHR data in order to inform ground models for wind farms? So if it were possible, then we would have better kinematics, so improving imaging of structures. Here you see a beautiful channel and channel filling sedimentary structures. And the broadband geophysical model, just like in telecommunication, broadband means you have a lot of information. Broadband geophysical model means you have a lot of information about the distribution of geophysical properties and therefore potentially soil properties, especially if we move to an elastic or viscoelastic approximation of the wave equation. You may even get information about shear strength, density, and attenuation. So is this feasible on UHR data? And in particular, I'm going to do like back of the envelope calculation of how much it would cost to do 3D full waveform inversion if we want a 1 meter resolution using a finite difference scheme. So because in 3D you have both the three spatial dimension, but also you have the fourth dimension in time. And if you want to sample properly your wave field, you need to reduce the grid spacing in space. You also need to do that in time to avoid problems of instability. So that means that your computing cost increases with the fourth power of the frequency. So what does that mean? That if your 50 Hz 3D FWI takes 24 hours to run, at 500 Hz, it will take the equivalent of 27 years. So this is just to say that full waveform inversion is an HPC problem. It is so in oil and gas, and it is even more so when we aim for resolutions that are useful for the kind of scales that we want to be looking at for a wind farm site characterization. In particular, if we want to do elastic modeling, we need to consider the VS in the shallow subsurface can be very slow and even as low as 100 meters a second. So that's even a stronger constraint on your grid spacing. I mean, it's not an unsurmountable problem. You can think of localized, target-oriented, optimized inversion, where after you do a beautiful 3D side-wide imaging as the one that Edward was showing earlier, maybe you focus on narrow corridors or areas around the planned WTG installations and you do a localized 3D in there. There are ways to optimize acquisition, but it's just to say that it doesn't come for free. And I think it's currently when you see very high res FWI, we are talking about hundreds of hertz. So in order for us to push it to kilohertz scale, um, we need a serious investment on numerical methods and HPC infrastructure, and also convince developers that this is worth the cost. And is it worth the cost? So can we actually, in streamer reflection data, where typically you have 100 meters, 200 meters long streamers, um, inform the subsurface model with the mid wavelength that we were showing earlier to get the broadband bare. So let's say you want to image this structure here. This would be probably a fair representation of what the scale would be with the length of the streamer towed by this acquisition vessel. So you have limited offset, you lack low frequencies. Let's see what happens if we do a full waveform inversion in these settings. In fact, what you get is a cycle skipped, so-called cycle skipped model, which means that you converge to a local minimum. And the reason is that the sensitivity kernel of FWI works at this depth, at this range of angles in the migration regime. It means that it's going to just fit the amplitudes, but without updating your mid-wavelength model. In order to do that, you need diving waves, just like you do if you do full waveform at a global scale or the regional scale or crustal scale. So in order for full waveform to deliver in this sort of data, you need to start exploiting reflections in a clever way. And for example, if ever a geophysical contractor is going to propose to you to do full waveform on reflection data, is most certainly going to use this, a reflection FWI kernel that essentially uses reflections explicitly as deep source of energy. So not only you have the banana kernel between source and receivers, but you have the banana kernel between two virtual sources that are places twice as the depth of the reflectors that you injected in the model. And only if you do that, you can update simultaneously the mid-scale, large scale, and small scale of the model that allows you to have a a picture of the subsurface that can be useful for imaging and for the derivation of then soil properties, for example. So just to wrap up this little initial section, so we must use a reflection wave path if we stick with the conventional way of doing a geophysical survey in wind parks. But this requires a perfect knowledge of the streamer geometry and depth, a good representation of the sea states changes, and you have no kinematic information about VS, at least not that come from the data. The only way you can access them is the amplitude versus offset. So I think as much as it happened, just like it happened in the oil and gas industry, it's my opinion that perhaps the not only reflection full wave inversion, but also the deployment of acquisition methods such as ocean bottom nodes, ocean bottom cables will be key if we um, in order to have a more robust um, reconstruction of the subsurface that is entirely data driven. So ocean bottoms, they're very expensive, but perhaps I haven't got an example in here because they're not used in wind farm characterization yet, but I think they will be. I don't know, that's just my opinion. Then full waveform inversion, moving to elastic. So say we don't want to limit ourselves to p wave velocity, although we only record p waves. So can we access shear moduli and density, because this is where the geotechnicians are going to be very happy. So there's this little guy here is the scattering pattern that weights basically determines how your residuals map into the subsurface for each parameter. So each missing heterogeneity of your model would behave as a virtual source that scatters with a certain pattern. So if two parameters scatter in a similar way, there would be crosstalk. So you cannot tell one parameter from the other. Another way to look at it is to look at the components of the first eigenvector of the sensitivity kernel. It basically tells you how much your inversion is sensitive to a set of parameters and how coupled they are due to this term here. So for example, in this VPVS density parameterization, because in a narrow reflection angle range, both density and VP have a strong contribution. That means they have a strong coupling, and this is typically seen when you do short offset FWI. You cannot tell VP from rho, and you get instead impedance. And at the same time, shear properties are almost not important at all. Whereas if you use, in this particular example at least, a parameterization based on impedance and density, you have a higher importance of shear properties, and density and impedance are better decoupled in the angle range that you have. Then you need to have the angle range. You know, don't always have that. But it's just to say that um, FWI, in order to deliver on a broadband and multi-parameter model, needs a proper parameterization study that is model dependent and is data dependent. Um, the sensitivity to changes in VP to VS ratio also is model dependent. And for example, these are four synthetic examples, very, very simple, just a toy model. There's an encasing medium and there's a layer with a higher VPVS. And the ratio between these two layers is always 5. So in the first example, the encasing medium has a VP to VS ratio of 2, and the small layer has 10. Then you have 4 and 20. So the ratio is exactly the same. But if we just do a simple synthetic, you see how in the low VP to VS ratio condition, so you're more similar to a rock, let's say, there's a big change in reflection amplitude versus offset. But if you move to a behavior more similar to a soil, it's very, very little. It's 5% and we are talking about reflection angles of 50 degrees. So we have to be aware of that. It doesn't mean it's impossible, But we need to be aware that FWI, when downscaling the FWI technology to shallow geological studies, the properties of the sediments change, and therefore your parameter sensitivity also will change. So for each survey, we have to ask the question, is elastic the right choice? Do we need a hierarchical approach? Or are elastic properties actually second order defect with respect to anisotropy or attenuation? Do we know well enough the source and receiver group directivity in order to invert for amplitude changes versus angle? So again, I suppose food for thought. It can work, but we need to know what we are dealing with and the physics. So a couple of examples. So this is very, very shallow study. So we are going to look at the top 6 meters. We are in Norway. It's 2D data, unfortunately. It's legacy is what we had at the time. And we were going to study the changes in properties in this very shallow and thin layer, which we can already see qualitatively is changing phase and amplitude around here. And so we're going to take the pre-stack data at these two locations, and we are going to invert them using a stochastic, in this case, localized 1D elastic waveform inversion with an estimation of uncertainties and see what we get. What is interesting here is that it would have been very hard in this case, and it would require us having partial stacks at different angles and so on, and heavy processing to do amplitude versus offset inversion. If we want to apply it to do an inversion on the raw data, this is the signal, and this is coherent noise. This is a receiver ghost because the streamer was stowed deep in the below the sea surface, and so you have this very strong negative polarity reflection that cuts through the event that we want to fit, matching the wiggles. And same here. So full waveform inversion, considering the sea state, considering the streamer geometry, and so on, in this case was the correct choice, in my opinion, to address the problem. And in this case, we invert for P-wave impedance and Poisson's ratio, and you see in the area where we have stronger amplitude, by doing full waveform inversion, we obtain also a very strong decrease in impedance down to almost 1.5, but also a decrease in Poisson's ratio, which is a signature of gas saturation. And how can we use that? We can feed this into a geoacoustic model, one of the many possible. And you can see that the gas saturation in here, the partial gas saturation, is very low or almost undetectable in the so-called site A with the low amplitude in here, whereas we can actually find that there is a non-negligible partial gas saturation in the area. So we turned this raw record in a sort of a virtual log of impedance and Poisson's ratio that is then turned into some measure of the physical properties. And then the last example, in here we actually compare amplitude versus offset inversion with FWI. The objective is to predict a synthetic CPT, so compenetrometer testing, at a location where the real CPT data has been withheld by the client. And in here you see the results of elastic impedance inversion with uncertainty is the black line and the shaded gray area, and the ground truth data that we want to fit is the red line. Of course, full waveform doesn't give you directly the CPT parameters. There's then a machine learning tool in between, but the quality of the input data is what determines then the quality of the prediction. So generally, we haven't got a bad fit, but we don't quite get the quantitatively the increase in tip resistance. If we use full waveform inversion, you see the predicted model kind of locks into the ground truth data, and this is precisely the effect of what we were talking about before, the fact that by using a full waveform approach and not a scale separation approach where you first do migration, then so first you do velocity analysis, then migration, and then AVO. In this case, you use full waveform, you get a broader band model, and broader band means more information and a more complete representation of the subsurface. And also we noticed that there was a reduction in uncertainties. But that's probably beside the point. So in conclusion, yeah, computing cost is a challenge, but it's not insurmountable, and it's an HPC problem. And if we convince the developers that this is worth it, then it can be a way forward. Reflection kernels should be used, and they are already, I'm sure, in industry, people are already using them. Perhaps multiple reflections and diffractions um, can be also used to increase the illumination of the subsurface, and ocean bottom nodes, as I was saying, to have more diving waves that can constrain your long wavelength. Then parametrization is really important, and uncertainties. But perhaps, in my opinion, the most open area of research is how to reconcile geophysics and geotechnics, as in now there's often a two-stage approach where you do a geophysical inversion and then there's some sort of machine learning tool that works on a training set data to do a prediction. But perhaps something can be done in the direction of direct inversion of the wave field for soil mechanical properties, or maybe that won't be necessary, and my question will be just surpassed by the new technological developments in machine learning and artificial intelligence, who knows? And that's it. Thank you.